Okay, we'll get started. So I thought I'd start by just giving you a quick summary of the feedback from the mini survey we did last time. Of course, we'll do formal evaluations later in the class. It's always a good idea to get early feedback. So just a quick summary of some of the items in terms of what you liked. You liked the video recordings, and now they are available at this website. Show them up there. So it's labeled by the day of the lecture. And I'd ask you not to share those, not to post that link, not to post the videos on YouTube, etc. At this point, we still have some editing to do. We have to cut the front and the back end, and we're doing that too, but I thought I'd just give you the raw video now in case you wanted to review any of the lectures. People like the book being free and PDF as well. People like the lectures being up the night before, which I have managed to do so far. You liked the videos in class. You liked the fact that I'm mic'd up. You like the colored cards. You like the idea there were no clickers for marks. Not taking attendance in secret ways. You like the applications and examples in the lecture slides so far. What you didn't like it when I used red or green on the board because you couldn't see it, which is a good point. I'll try just to use black. Good contrast. Sometimes I speak too quickly. Sometimes I speak too quietly, so I'll try to slow down and speak up. Someone complained there was no PDF of the book. They obviously hadn't been reading the Connect website where I posted the PDF, thanks to popular demand. Someone complained the lectures were too long to print. Well, print them 4 up or 6 up on a page, and you'll save, and two-sided. You'll save lots of forests that way. A legitimate point is some of you didn't like. Couple, you didn't like the hard copies and soft copies of assignments being submitted. I explained the reasons for that. The hard copies are because that's what the TAs mark on, and sometimes we can't print your obscure file formats that you submit, so it's just easier if you print it. And we need the soft copies just in case, to protect you against plagiarism and things like that, of course. But it also is, it's like belt and braces. You can prove that one was submitted in time, then you're okay in terms of lateness. Those were the main points. I haven't had time to analyze them in detail. I will go through it more carefully and summarize more carefully. But again, if you have any suggestions for how you'd like the class to change, either put it on Connect or just email me privately or come and see me. I apologize I wasn't in my office for the last office hour. I was here giving an office hour with a whole bunch of you talking about states and features and relations. But that's it in terms of the summary. So just a couple of points about how to get the most out of the course. We put both on the schedule on the home page and on each lecture, I put the section in the textbook you should read. And I really think you'll get more out of it if you read it before the class. Of course, you'll get more out of it if you read it after the class than if you don't read it, but you'll get it more out of it if you read it before, because I think it'll give you a much better context. You'll be ready to understand quickly, and so on and so forth. Oh, in fact, I missed a point on the negatives. Some of you thought that I went too slow, and some of you thought that I went too fast, of course. I think there were more too slows than too fasts, so I'll take that as an indication you'd like me to go a little faster, but I don't want to leave anyone behind, etc. So if you are having that problem, talk to me, and I'm willing to spend extra time with people if necessary. So you read ahead. You can do it your own way, but what I would do if I were taking the course would be to print out the slides, 4 up, two-sided, before the class, but not read them through. Read the book through, but don't read the slides through, because the slides have answers to the colored card questions, and I think it helps to work them out in your own head rather than to read my answer. I usually put the answer, I don't always. I do try to make clear, and someone complained I didn't always make clear what was the right answer to the question. But I do try to make that clear in most of the slides. So I don't think reading ahead through the slides is a great idea. Read the book section first. That's just my idea of how to get something out of this course. And we will, people asked for exercises, which we will be posting, not for credit exercises, which will come up as we get more into the course, that you can try on your own. Questions? Yeah. Yeah. Yeah, they're coming. Yeah. Any other questions? Okay. So today we're going to talk more about search, which is sort of said fundamental to AI. Because you often have to generate solutions or possibly partial solutions. Better if you can generate partial solutions and reject them if they're not going to lead to a full solution, because AI is like that. You know, there are many different possible solutions. We're solving inverse problems, not direct problems. Okay, we don't have direct algorithms for any of the problems we're trying to solve in AI because we're trying to solve really, really, really hard problems. So search is fundamental. That's why we're starting with that in this course. We're going to talk about uninformed search. We've talked about generic search before. We're now talking about uninformed. What this means is an informed search strategy would be one that, first of all, knows the costs of the operators, knows that some things are cheaper than others, and secondly, has some idea what the goal is, where you're going to. Okay? Uninformed strategies have no sense of where you're going. You know, it's not like, oh, you're getting warmer, no, you're getting colder, you know, that kind of game you play as kids. It's not like that because you don't know where the goal is. You don't know where the goal is until you stumble right over it, until you expand it off the frontier, look at it and say, oh, great, I found a goal. I finished. I pop back up. That's what an uninformed strategy is doing here. Okay? There's no sense in which the goal is informing the strategy. And those kinds of information we'll call heuristic information, which can vastly speed up the search in many cases. But these are your default strategies if you have no information about where the goal is, or how to get there, or what the costs of the operators are. Okay? So there's two famous standard strategies, depth first and breadth first, which we're going to talk about in this class. And I'm sure many of you met these in various guises in various other courses. So this probably won't be new for many of you. But again, we'll always do this little review, and most of you like this kind of mini review of the previous lecture at the beginning of each lecture. So we talked about search being a key component of many AI agents, and we're going to study basic principles using this simple model, deterministic, which means that whenever you do an action, exactly that thing will happen in the world. You know ahead of time what will happen in the head of the agent, you know, you being the agent. It's trying to achieve a goal. It may not be informed by the goal, but you know you're trying to solve a goal, and it's a search agent model. So we have this generic approach where we define a search space graph. We talk about the frontier, initializing with an empty path. It's empty because we just have the start node on it. We don't even have an arc from the start node to the next node. And we incrementally push out the frontier until we reach a goal state. So think of the frontier as the set of paths. Okay, although we often show them as nodes. And if you think about it in a tree, the set of nodes on the frontier is isomorphic. It's one-to-one with the set of paths. For each node on the frontier, there's just one path that leads to it. This is one-to-one correspondence, right? So that's why we sometimes use them interchangeably. And for now, as I said, we're going to think about the search space being a tree. And then we'll worry later about cycles and all sorts of nasties. Okay? And the way in which you push out on the frontier is the search space strategy. So we gave this nice example of a robot cleaning a couple of rooms. And there are 8 possible states of the world. 2, 4, and 2 is 8. So these are all dirty rooms. These are half the rooms are clean, and these are all clean. So notice there's sort of a monotonic progression. Rooms can only get cleaner. They can't get dirtier. And the goals are these 2 nodes down here. And so each operator We use operators and actions interchangeably when we're talking about deterministic actions, because every time you apply an operator to a state, you get to a new state. It may be the same state. Try to go left here and just bump into the wall and stay where you are. But if you suck the dirt here, you will get to this state where it has no dirt compared to dirt, and everything else is unchanged. Okay? So this gives you the all possible ways in which you could move around this search space, which is really a state space in this case, because we're showing each state explicitly. So it's a finite state space. So this is our frontier idea, and again, these are the nodes on the frontier, but for each node there's a path, a unique path back to the root, which is the start node in this case. Okay? So we're thinking of these paths as being on the frontier. And we had this generic search algorithm, but I've deliberately thrown in a few bugs here. So we have to debug this algorithm to see if you remember the true search algorithm. So we take in a graph, a set of start nodes, and a goal procedure that tests if it's a goal. We set the frontier here. While the frontier is not empty, select and remove a path from the frontier. If it's a goal, you return the path. Otherwise, find a neighbor and add the neighbor to the frontier. Is that right? No? Where are there any bugs in this? I hear there are some bugs. Shout out a bug. Frontier here shouldn't start with a goal node. What should be there? Should have a start node, S, where S is a start node. Okay, that's one bug. Are we done?
It's not find a neighbor, it's for all neighbors.
Okay, so you've got this, you're looking at this path N0 to NK. This is called expanding the node here. This section we'll call it expanding the node, and here you want to, of course, consider all neighbors N of NK, right? So that's a bug.
Then you don't add the expand.
And you don't just add the node, we want the entire path going to that neighbor, right? So there's the bug start at the start nodes, add all the neighbors of NK to the frontier. Of NK here, all the neighbors N of NK. Add the paths here to the frontier, not just the nodes. So this is the one and true generic search algorithm where we fix those bugs. That's why it's a good idea not to read through the notes ahead of time, because it's better to sort of do that online. Where I think we understand that now, as I say here, think of this. We call that expanding the node. In fact, right here, we're selecting and removing this path. We're examining this node to see if it's a goal. If it is, you're done. But return the whole path. Otherwise, expand it. Okay? So this is where you're processing this path. And it's not until you're removing the path from the frontier that you check to see if this node is a goal. Notice that? You could imagine in this step here, when you're pushing these neighbors of N paths onto the frontier, maybe you should look for the goal N when you've generated them. No, that's a very bad idea, because you lose certain algorithmic properties, as we'll see. You might get there a little faster, but you'd lose certain guarantees, which we need. We want to prove properties of these theorems. So you don't even look at the path until you take it off the frontier. Check to see if it's a goal. If it is, you return it. Otherwise, you expand it. Okay? That's a key point. Okay, so we're done with the recap. So depth first search, I mean, it literally means you go down the depth first. When you hit a dead end, you back up to the last choice point, come down here, back up, come down to there. We haven't found a goal yet, so we have to back all the way up to here, and then come down there. Oh, sorry, would have come back down there, 12, 13, 14. This numbering is very important to, again, this represents when we take it off the frontier, not when we generate it. Okay? So eventually, this might be the current state. We've expanded 16 nodes. We're at this point. Notice when you expanded one here, you put these two nodes on the frontier, or these two paths on the frontier, right? And similarly, when you expanded this one, you put these two on the frontier. So this path will still be on the frontier. This path will still be on the frontier. This path is on the frontier, and this path is on the frontier. Okay, so I've got 4 paths waiting on the frontier. But I always go back to the last one generated to figure out which one to expand next. Okay? So it's last in, first out. The last thing I generated that's still waiting to be expanded, it should come off the frontier next. So this guy will wait for a very, very long time before you've explored all that. Even though it was generated on the first step, it's still waiting there while we explore this whole left-hand side of the tree. Okay? So, frontier of the shaded nodes, we're going to ask which node will be expanded next. So as I said, read this definition of expand as remove the path ending at node from frontier and put its successors on. That's what I mean by expanding a node. So if this is the frontier, we're looking at these nodes, these 4 nodes. You've got your cards ready. Okay. This is the frontier. So which node will be expanded next? And if there's any doubt, you expand left to right. Okay, so you think of the successors of putting on the queue in the left to right order. Question? Yeah, you've got a card up. Okay. I see lots of undecideds. Okay, so we've expanded this node. So when we expanded 16, we put this path down to here on the frontier, and we put this path down to here on the frontier. So these two have just gone on the frontier, right? We've already expanded 16, so it's not that one. As I said, if there's a choice, choose the leftmost node. We'll assume these successors are ordered. So this one, yellow, okay? Which most of you got, but not everyone, so we're not getting it yet. Any questions about why it's that one? No? Okay, let's try another one. Suppose this is a goal. We're still here at 16. We've expanded 16, so this is our current frontier with those 4 nodes on it. Let's say this is a goal here. Okay? We don't know it yet. We haven't got there yet, but we know it's a goal. How many more nodes will be expanded from this point on? Think carefully about that. Think exactly about what I said about what it means to be expanded. Okay? We've got these 4 nodes on there. We don't look to see if a node is a goal until it's expanded. Remember that. We do not check a node to see if it's a goal until it's expanded. Okay? So let's think about it. We've got this frontier, right? The last one on is the first one, expanded, so we're going to expand this one. But it has no successors, and it's not a goal. So we've expanded it. We've now got 3 paths left. That's one node we've done. We've got 3 paths left. We now expand this one. Okay, that's 2. And we generate this one. This is now on the frontier along with those 2. We've got 3 paths on the frontier. Now, this is the last one generated, so we'll now expand it. That's 3. Okay, I'm hammering this point because you have to realize that you don't check to see if a node is a goal until you expand it. Okay? So if you don't understand why that's a 3, you have to go back through the last couple of slides, read the book, etc., etc. That's a key point. Okay, most of you got that. 3, you only return once the goal is being expanded. Okay? Not when a goal is put onto the frontier. So even though that is a goal, and I've generated it, and I put it on the frontier, I didn't bother looking at it. I don't know it's a goal until I take it off the frontier and inspect the last node in the path and say, bingo, I got one, I will return it. Okay? Any questions about that? That's the key point. Okay, so obviously the only change we have to make to our generic search algorithm to make it depth-first search is to look at how we treat the frontier. I mean, I just said here select, and according to this we could just select any path from the frontier at random, and that will in fact usually work. But if you want depth-first search, you should select and remove the last generated path from the frontier first. Okay? So in depth-first search, the frontier is a last-in, first-out stack. So you could implement it as a list by just pushing paths on the front of the list and popping them off when you want to expand it. Right, and the guy right at the back end of the list, which will be this path, you won't get there until you've investigated all the possible routes on this left-hand side of the tree and got back up to there. Okay? So this should be relatively familiar to you from your algorithms class. I mean, you can implement this stack in various ways. You could actually use the stack of the programming language you're using by just popping on recursive calls and popping them off. Or you could explicitly have a data structure in your language representing, say, as a list, the set of all paths. It doesn't care, I don't care how you do it. It's just an abstract data type. We're going to push and pop on this stack, which is the frontier, until we've exhausted all the paths. Okay? So let's analyze it. We want a few properties of algorithms. We want things like completion. We'd like it to terminate. We'd like it to be optimal, etc. So let's see what properties we can prove of depth-first search. We define a search algorithm to be complete if, whenever there is at least one solution in the graph, the algorithm is guaranteed to terminate and find it within a finite amount of time. Okay, so is depth-first complete? Yes or no? Yeah, question.
There are no cycles?
Well, you can assume whatever you want. You know, the beauty of this question is you get it right either way. It's complete and it's not complete. Depends what you assume about the search graph. As I said, until now we're assuming the search graph is a tree. And if it's a finite tree, like this one, obviously it's complete. The answer is yes, for finite trees. However, you know, if this were the search graph and I chose to come down here first, then if I'm using depth-first search, I'll just keep expanding this path. It'll just keep getting longer and longer as I push it on the frontier. I'll never get out of that cycle. So obviously the answer is no if there are cycles. Or you could think the answer might be no. Even if it's a tree, it could be an infinite tree. There could be a huge infinite branch all the way down here that goes on forever. And the goal is over here. Right? And I haven't said the search spaces are finite. You know, you could imagine, I don't know, like putting pennies on a stack of pennies. You could just keep putting pennies on it until you run out of pennies, which you would never do, maybe. Right? So yes, if you assume the search space is a finite tree. In all other cases, no. So you win both ways. Provided you give me the, if this were an exam question, you'd have to say yes if it's a finite tree. Otherwise, the answer is no. We want optimal algorithms. Is this optimal DFS? If when it finds a solution, it's the best one. In this case, what we mean by best one is the one at the with the fewest number of actions, right? Is it optimal? I think most of you see that it's not, because you can easily construct a counterexample. You know, if I had only 2 goal nodes in my finite tree search space, these 2, then this one would be found first. So it says when it finds a solution. Okay, it's found a solution here by depth first before it found this one, because it hasn't expanded this node yet. And this is much worse than that one in terms of depth. So the answer is no. Complexity, we're interested in time and space complexity. What's the time complexity? We're always worst case. It's expressed in terms of the maximum path length and the maximum forward branching ratio. And if you consider the maximum forward branching ratio, you might as well consider every node to have the same branching ratio, B, and all depths to be uniformly M. So what's the time complexity of this algorithm under that assumption? Again, consider the worst case. What's the worst case for DFS? It's when the solution is over here in the right-hand corner, right? It'll have to search the entire tree before it finally gets to the solution. So always consider the worst case. It's going to be B to the M because I've got one node there, B nodes there, B squared, B cubed, B to the M. It'll have to look at all of those in order to find that solution. Okay? B to the M. Using that single goal node. Okay, so what's the space complexity of DFS? This is where it gets interesting. You probably know the answer to this if you've taken an elementary algorithms class, which I think you all have. The space complexity, define it. It's the worst case amount of memory that the algorithm will use, i.e. the maximal number of nodes on the frontier, expressed in terms of maximum path length and maximum forward branching factor. So we could use this as a model. Here's our frontier. So we're interested in how big can the frontier be in depth first search? How bad could it get? All right? I mean, so imagine, suppose I'm coming down here. Suppose I'm down here. I've expanded all the way to down here. And at each point, I've got B nodes coming off, right? And I'm taking one of them, but there are B minus one of them left. B could be very large. So at each stage, I could have B minus 1 nodes waiting on the frontier, right? They're hanging about waiting because I'm right down here and I've got all these open possibilities I might have to backtrack to. Backtrack means go back to the last choice point, right? But it's not bad. It's not exponential, right? There are M levels, B at each level, M times B. Green. Some of you got that, but not many. So think more carefully about it. But as I said, this is the explanation. The longest possible path is M. And for every node in that path, 1, 2, 3, 4, down to M, you must maintain in the frontier a fringe of size B. Well, it's B minus 1, but this is all worst case, large numbers, so we'll assume B, B minus 1 are essentially the same. Because when we're doing order of complexity, we don't care about lower order factors. Is that okay for people? The key takeaway is that in depth first search, the stack doesn't get very big. It's linear in the size of the problem, both the branching ratio and the depth of search. That's a huge win. So if you have a reasonably small amount of memory, that first search is often the best way to go, provided it doesn't have cycles in the tree, et cetera, right? So that's the lesson there. Is there any question about that? So you look a bit puzzled. Hardly anyone got that point. It's written up in the book. Okay, so our friend, the obvious counter to depth first is breadth first. And you can think of depth first as being really adventurous. It's like the greedy algorithm. Breadth first is incredibly conservative. It just goes down one level at a time. Ka-chunk, doesn't leave anything behind. That's the way I think about it. So here's breadth first search. Again, these numbers do not represent the time at which it was generated. They represent the time at which it's expanded by being taken off the frontier. It's not when you push it on, it's when you take it off. Okay? So you can see it's very conservative. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're right here. We've just expanded this one. So our frontier consists of these 3 nodes and one level back, these 3. So in the frontier, I either have all the nodes at the same level, the paths end in nodes at all at the same level, or they're just one level apart, staggered like that by one level. It's never the case that any other situation can happen on the frontier in breadth first search. So you never, no nodes left behind. What do you think about it? And obviously, we just take the same data structure frontier and specify this select to be first in, first out, or last in, last out. Call it first in, first out. A FIFO queue. So that means you could implement it as a list, and you could push them on the back end of the list and pop them off the front end. I don't care how you implement your queue. There could be better ways to do it, with a balanced tree, etc. But probably it's overkill in most cases. So that's the only difference for breadth first. The frontier is a first in, first out queue. So whenever you're just trying to decide here, I'm trying to decide which one to expand, then this one, of all these paths, this one was the first in, so it's the first out. I will expand that one next. It has no successors. So it will become 17. Then I will expand this one. It'll produce these two successors. It'll become 18, and so on. I just work my way across the rows at the same level, expanding them. Remember what those numbers mean. That's when I expand it. So the search algorithm is complete, again, as with depth first, which is complete for a finite tree, but otherwise incomplete. Is this algorithm complete? If there is at least one solution, the algorithm is guaranteed to find it within a finite amount of time. Is it complete? What do you think? Yeah, I think that's fairly clear. Of course, I'm going to ask you to prove it. It is complete. How do you know it's complete? What would a proof sketch for this be like? I mean, it seems so obvious that you couldn't be asked to prove it, but we might want to prove it. Any ideas? Well, in order to prove that, we probably have to put some limitations on it, like B is finite. The branching ratio is finite. That might be a good idea. It wouldn't be clear. But if it's finite, so you're generating a finite graph, and if there is a solution, because you're so conservative, you really can't miss it, right? I mean, it's probably better to look at the proof sketch for optimality. Optimality says an algorithm is optimal if, when it finds the solution, it is the best one. And by best here, I mean the shallowest, the least number of actions required to carry it out as a plan. Again, we could consider these two. Suppose you had these two goals. Right, two goals. This is, again, pretty obviously optimal, I think. If you think it's not, maybe you could give me a counterexample. It doesn't find, yeah.
What happens if your victory states or goal states are 4 and 7?
4 and 7.
First search finds 4 faster than breadth first finds either of them?
I didn't say faster. So optimality, I'm not comparing it to depth first. I'm just saying when I find it, the first solution I find is the best solution. Now, there may be more than one best. Yeah, 4 and 7 were both solutions. I don't care which one because they're both equally optimal. Okay, so maybe that's what people are thinking about. There may be more than one best one, but that's okay. We'll take either one. Okay? So what would a proof sketch for that look like? If I were asked to prove this, I'd probably do something like this. I'd want to prove it by contradiction. So I'll have a theorem. Breadth-first search is optimal. Proof sketch. By contradiction. When something is blindingly obvious, sometimes it's so obvious you can't think of a proof. It doesn't sound ridiculous. Like the theorem is true because it's true. That's not really a good enough proof sketch. The way I find easiest to do it is to suppose it's not true. So I'm proving it by contradiction, which I'm sure you've met before. But so this is a hypothesis. Suppose node G1 is optimal. And by optimal, I mean least depth. Can you read that? Oh, you won't read that. And BFS finds some other node, G2, first, where depth of G1 is less than the depth of G2. Okay, so if breadth-first search is not optimal, then I must be able to. If this theorem is not true, then I must be able to conjure up this situation where I have node G1 is optimal, it's at the least depth, and breadth-first finds some other node, G2, first, where this one, G1, is at less depth than that one. Right? But by BFS, G1 must be expanded before G2, hence found first, because when it's expanded, we'll check to see. Hence, contradiction. QED. QED means proved, quod erat demonstrandum, that which was to be proved, QED. The proof is done. I mean, it's a trivial proof, but it's a sketch, and that's the kind of thing you might have to do on an exam, if I were being mean. I mean, occasionally we have little theorems to prove. Okay, does this make sense? So what about the complexity of breadth-first search? This is pretty straightforward. Again, it's worst case, time. In space, we're interested in here, it's time. Again, maximum path length is m. Maximum forward branching ratio is b. Assume it's the same at every level. What's the time complexity in terms of m and b? Get your cards out. Wake up, Friday afternoon, thinking about the weekend. No. Party time, time to go to the beer garden. I'll let you out in a few minutes. Sunny out. So the problem with BFS is it explodes, right? I mean, you're doing everything. This is going to be, there's one node there, B nodes there, B squared there. We've got to look at them all before we get to a goal, right? So once again, if there's one node down, if there's one goal down there, you're going to have to look at every single node in the entire tree before you get to the goal. And we know there are b to the m nodes, so that's the time complexity. So that's no worse than depth first search, so okay. But the space complexity is much worse. Remember, the space complexity in DFS was linear in B&M, right? But because we're maintaining this humongous frontier consisting of all the nodes at a level or at the level and the level behind it, the frontier is going to go very, very large. So we have a space explosion. So how many nodes at depth n? Order b to the m. That's the size of the frontier, right? So the problem with breadth first search is even if a problem could be solved in less than exponential time, breadth first search will always take exponential time. You know? Not good. However, you may be forced to use it sometime. And so we have some now that we've done those analyses, we've got some ideas. When would it be good to use depth first search? When would it be good to use breadth first search? If you don't have any other information about the problem. And we'll see we can do much better than both of them as we get into heuristic search. So get your cards out and answer this question. What's the best algorithm when you've got cycles or an infinite search graph? Be cautious, because you've got cycles. You might get stuck in them with depth first. So go breadth first, right? Most of you got that. When you need the shortest path to a solution guaranteed, which one should you use? Shortest path. Okay, most of you got breadth first. That's good. If you're not getting these answers, you missed something in the lecture. We'll go over it again. What if there are only solutions at a very great depth? What would you like to use? Remembering the time and space complexities of these two algorithms. Okay, good. Most of you got depth first because you can only afford, you can't use this. It'll just blow up on you. The space and time complexity is exponential. You'll never get there if they're really deep, like hundreds of pi deep. Depth first has a chance of getting there. You may not get there, but at least you've got a chance. You have no chance with BFS. What if you, and that says you know something about the problem, but you don't know where they are, but you do know they're all very deep. And we know that for some problems. Other problems might have some solutions at a shallow depth. What would you use? The other one. So you use depth first here. If they're only at that depth. If some are shallow, use breadth first. Because if some are shallow, they might be in the left half of the tree, and depth first will miss them. They'll go really deep and lose out. Breadth first so cautious, it doesn't matter which side of the tree they're on, it'll get them before you go any deeper. What if there's no way the search graph's going to fit into memory, the whole thing? You have to generate it sort of on the fly. And this is where the linear space complexity of DFS comes in. Use it. If you're starting to run out of memory, and even terabytes won't solve the problem. Yeah?
Explain why the space complexity for BFS is also exponential, like that.
Space complexity of BFS? Right here. The point is, if there's a solution, if there's only one solution down here, right? Then the frontier just keeps getting bigger. Every time you go down a level, the frontier increases in size by a factor of b. Because there are b times as many nodes on this level as there are on this level, right? So the frontier at this level is b squared, b cubed, b to the m down at this level when you hit the solution. Okay? Because the frontier is maintaining every possible solution up to that point. It's guaranteed to explode on you. Okay, so this gives us an example where we're trying to solve Sudoku. And now we know we could write an algorithm now to solve Sudoku using breadth first and depth first search. Which one would you use? What's the characteristic of Sudoku? Well, we've got 9 by 9. That's 81 squares to be filled in. That's 81 actions. So m, the depth, is 81 minus the ones that are already filled in. I don't know how many there are, 20 or so? So maybe it's 60. M is around 60. What's B? 10, 9. You've got numbers 1 to 9. So at every square, you could put in one of the numbers 1 to 9. So what's 60 No. 9 to the 60. Say that again? What? Yeah, you don't count these guys. Yeah, I took those out. I had 81 minus 20 is about 60.
The numbers you can put in the box isn't all 9 because of the rules.
No, I know, but when you have to check them out, and then you say, oh, I can't put that one in because 9, that would fail at that point, right? You have to check it. Okay, so you have 9 to the 60. B to the M is the size of the search space for breadth first search. All the solutions are at the same depth. There's 60 down there, right at the bottom, 60 levels deep in this tree. There are none earlier because you got to fill in all the 60 squares, right? You see that? So which method would you rather use? You've got to use depth first. There's no way, I don't care how many terabytes you got. You're not going to get away with breadth first. You've got to use depth first. What about this one? You're trying to solve the 8 puzzle. Again, we don't know how deep the solutions are. We don't know how far it is to get from there to there by moving the blank around or moving the tiles. So we don't know the depth in this case, whereas we knew it was 60. M was 60 in the last one. We don't know how many moves it's going to take to get from there until we solve the puzzle. And then we solved it, so we don't care. So, but there are other characteristics of this problem that might suggest you use one or the other. So which one would you use and why? Yeah.
You have to use BFS because there can be cycles.
Because what?
There can be cycles.
Yeah, you've got to use BFS because there could be cycles. I could move this square to here, and then move to this, there, to there, and then keep doing that. I'm not making any progress in solving the puzzle, but I've got a cycle in my search graph. So, I mean, there are better ways. In depth first search, you could check for cycles, and we will do that later. But if you've just got these two dumb algorithms that aren't even checking for cycles, and they're faster because they don't check for cycles, then you have to use BFS here, right? Okay, so this is what you've learned. You didn't know it, but you know all these basic properties of search algorithms: completeness, optimality, time and space complexity. You know how to choose the most appropriate search algorithm for these problems. And what you should do is read section 3.6 on heuristic search, and have a great weekend.